It's okay.
Yes.
All right. We did some diode exercises using mostly series circuits. I think also parallel circuit. We will continue on the diode application. We are in the part of the diode chapter where you will see some most common practical applications of a diode. So today we start by rectifiers. You have two types of rectification. One is called a half wave, the other one is called full wave. Also, there is a circuit known as diode clipper, which is a type of rectification. First, let me explain to you what is meant by rectifier or rectification. You will study in more details about this when you go to the chapter after the midterm known as power supply. The power that comes from our main line, it is coming from the AC current, alternating current. So I'll try to draw here. Let me find a white space where I can draw. Maybe on the right hand side. The current comes like this. This is an alternating current, a sine wave. But most of the devices that we use, finally at the end, they're using a DC level. So for the sine wave, one positive peak and one negative peak is one full cycle, which means you have two half cycles. Here is a positive half cycle, 180 degree, and another 180 degree is the negative half cycle. Totally 360 degree, one full conduction. So the voltage changes direction. Half of the time it is positive volt, so plus minus, and the other time it's negative volt, minus plus. If you connect an input AC source here, where I'm now drawing the arrow, input voltage, look at the polarity. Plus, the ground here is minus. Look at the diode, plus, minus. It is now forward bias. No material symbol is provided, so ideal diode short circuit. And then the path is closed. You have a loop from on the left hand side. The output voltage is how much? If you take output voltage from these two terminals, plus minus, it is VI, because ideal is 0 volt, VD is 0. So VI minus 0 minus V out equals 0. Therefore, V out equals V in. See the equivalent circuit on the right hand side. If the diode is forward biased, it is now closed switch, short circuit. So the voltage which is shown across R, which is also your V out, is same as the input voltage. Here Vn is the maximum value of the input peak. It's a sine wave, it's not a fixed value. 0 to T half, which means half of the period you have a positive peak showing up. Now, what happens in the next half cycle? In the next half cycle, the input sine wave is a negative current, negative voltage as well. Minus, and then polarity change to minus plus. Now, is the diode on or off? Will it conduct? Can the diode conduct? It cannot conduct. It is reverse bias now. Look here, open circuit. Switch is open. No current can flow. So there is no current flowing through R, which means you try to take a voltage, you will get 0 volt. So what happens to the output now? Flat, 0 volt. If you take the output from a half-wave rectifier circuit, the voltage output is like this. One half cycle has a voltage, the other half cycle has none. Is it very useful at the end? No, not too much, because if you want to provide constant output to a device, it doesn't make sense if the device keeps turning on and off, because half cycle, first half cycle, there is turning on and the negative half cycle it's off. You need output for a full 360-degree. By the way, the output is actually, it is not an AC, it is DC. It does not change value from zero, like positive to a negative. It does not cross the zero line, but it looks like an AC waveform. It is actually not alternating current anymore, in the sense that it doesn't go to the negative part, but it has peak and valley. It has a swing. It has a DC level, which you can find through a formula. So from this peak, what is the value of DC? It is 0.318 times Vm, the peak of the AC voltage. If it's 10 volt peak, it will be 3.18 volt DC, because you multiply by 0.318. Peak inverse voltage. We talked about this one. This is the maximum negative voltage allowed through a diode before it breaks down. As you can see, the diode here, in the positive half cycle, it is forward bias. In the negative half cycle, it is reverse bias. What is happening at the negative half cycle? At this point, the diode is sensing a negative volt. Even though it is not conducting, the negative volt is here. If the diode peak inverse voltage, let's say it is -5, the value, and this peak is -10, on the negative side, the diode will burn. That's why when you put an AC input to the diode, you must make sure that the peak inverse voltage rating is greater than the peak AC voltage during the negative peak. Say you have 10 volts peak, which means 20 volt peak to peak. Positive peak is +10, negative peak is -10. Your peak inverse voltage rating must be greater than -10, which means -11 or -12. If the input voltage exceeds the negative breakdown voltage zone, then you will damage the diode. So the circuit will be gone. During designing a circuit, you have to know the diode's PIV rating. Definitely from the spec sheet. It is given on the spec sheet for all diodes, and design your input accordingly. Now there is something called a full wave rectification. What does a rectifier do? It takes an AC input and converts into DC level. So your input voltage, can everyone see VI? I'm circling.
Yes.
This is the input sine wave AC. You see the peak, positive half cycle, negative half cycle, and the amplitude is Vm. This is the capital T is the period of one revolution or one cycle. Half T is where you have the half of the peak already coming in. So it's VI versus T graph, voltage versus time. It's a time function. If you have a full wave rectifier, what happens? Now we are looking at V out as a function of time. During the positive half cycle, you're gonna get an output voltage like this. During the negative half cycle, you will also get an output, which means it is always on. The associated DC level is 0.636 times the peak value. This is more useful. However, if you want to make the output a completely flat DC, you have to add more circuits, which is not part of this before the midterm. After the midterm, we will see how to do that. The formula for rectifiers, the DC levels, I think is given on the formula sheet, if I'm not wrong. I said in the first class, 95% of the formula are given on the formula sheet, but some are very fundamental that you have to remember by yourself. How do we achieve full wave rectification? If we just have a diode like this, just one diode, it is on only at one half cycle, off at other half cycle. It's not possible. One of the ways of achieving the full wave rectification is to use 4 diodes in a bridge configuration. This is called the bridge circuit. See how the diodes are connected, D1, D2, D3, and D4. And then you have the load in between the free nodes, load resistor R, the voltage shows up across, the output voltage is taken from across the resistor. So this is the V out that is showing across the resistor. And you have V in. Now start tracing the input voltage path. During the positive half cycle, which means input voltage here plus, minus, which diode will be on? Let's try to trace which one is going to be on. Is D1 on? What's the polarity? Do you think that D1 will be on?
Off.
Off. So how about D2? Yes, it's positive to positive, positive to anode. On. D4? No, it cannot be, it's cathode. And then going all the way to R, is D3 on? D3 is on. Positive polarity, relatively positive polarity applied to the anode. And you see where is the cathode of D3? It's negative voltage to negative. So during the first half cycle, the path is completed by diodes D2 and D3 in this circuit. The other ones are off. There will be a voltage showing up across the resistor of the load, which is this one. Now see how I trace. This is the path of the current flow. Then you have a negative half cycle. During the negative half cycle, let me zoom a bit. The polarity on the input side changes. Now it's minus, plus. So which diodes will be on? Let's clear this thing and retrace our path. Now I'm going to change this to minus and this one is plus. For the plus polarity, as you can see, D4 anode here, it needs a plus. The minus side is here. Can D2 be on? No, it cannot be on. So going through resistor and plus again anode of D1 and then out through D1. Just like here, the path is traced with the arrow. So the other two diodes are on during the negative half cycle. One pair will be on, the other will be off, and vice versa. During the negative half cycle, you get the second peak output. When you combine the first and second pairs and the associated outputs, this is what you get. This one is called a full wave rectifier. What is the DC level? Given by 0.636 times the amplitude, the peak value of the input waveform. This is one of the applications of the diode. Actually, inside all rectifiers, there is either 4 diodes or sometimes you can have less diodes. Is this the only way of doing full wave rectification? 4 diodes? No, this is not the only way we can study in this course. There is one other way. You can use 2 diodes. How? This is full wave rectification with 2 diodes. Same idea. You have an input sine, you want an output for both of the half cycles. How do you do it? This thing is called a center tap transformer. Do you know how a transformer works? There's a primary side, some coils. There's a secondary side. The number of coil on the primary side is given by N1. The number of, how to say, windings. As you can see here is 3, I think. The number of windings on the secondary side is given by N2. The primary side voltage is V1. Secondary side voltage is V2. the ratio goes like this: N1 over N2 equals V1 over V2. If you want to find the current, the ratio, it is N1 over N2 equals I2 over I1. For the current, the numbers reciprocate. So here it is showing 1:2, which means it is actually a step-up transformer. What is a step-up transformer? It takes an input voltage, and on the secondary side, the voltage is increased. If you have a step-down transformer, the primary side is higher, the secondary side is lower. This one is a step-up transformer. If you have 1 volt here, on the secondary side, you're going to get 2 volt. But what's a center tapping? The secondary side is actually basically one long coil with so many windings, but the center is connected with the load. This connection we call the tapping. It becomes a center tap. When you center tap the coil of the transformer, the whole side, the whole output side is divided into 2 parts. Each part is acting like a half cycle. Any questions?
No questions.
Okay. So what happens during the positive half cycle of the input voltage? You have positive and you have negative on the bottom, but since you center tap, this point becomes negative, again separated again to the second side. This one becomes positive since this is the ground. Which diode is on? Positive half cycle plus with diode's anode. D1 is on. What about D2? Will it be turned on? No, because it's negative with the anode off, open switch. Positive half cycle, this loop only is active, and you get the output from the positive half cycle is the first peak. What happens during the negative half cycle? During the negative half cycle, it is given on the bottom part of this slide. Let's do a negative half cycle. So overall, on top you have negative voltage, and on the bottom you have positive. But because of the center tapping here, you have to assign the polarity. So here will be plus, this one will be minus, the opposite of what already is. Negative, this diode is off, switch open. But this is positive, and this diode was originally like this, which means forward biased. And then from plus to minus, it will flow counterclockwise. The bottom loop is active, and voltage is showing up across R. Vi minus R equals 0, or Vm minus R, Vr equals 0. Therefore, what is Vr or Vout? It's Vm. This is the second peak. You combine them. After you combine them, what do you get? You get the final output. Full wave rectification by just 2 diodes and the center tap transformer. All in this case, this slide and previous slide with the bridge rectifier, we assumed ideal diode. If it was a silicon diode, what would be the output voltage? Assume both diodes are silicon diodes. What will be the output voltage? Vout equals, any idea?
(0.636 VM minus 0.7).
That is the DC level. Okay. Yes. This is the DC level. If you talk about Vout, it is Vm minus 0.7. Here the slide it says summary of rectifier circuits. If you have half wave rectifier, VDC is 0.318 Vm. If realistic silicon diode, the output you have to deduct 0.7 because there's a 0.7 voltage drop when you solve the KVL loop using a silicon diode. For a bridge rectifier, 4 diodes, VDC, you know the formula, 0.636 Vm. Realistically, 0.636 times VM minus 2 times 0.7 volt. Why 2 times? For the bridge. For each half cycle, how many diodes were turned on?
2 diodes.
2 diodes were on. Just one pair for the bridge, which means the voltage will be dropped by 0.7 volt 2 times. Across the path, there are 2.7 volt drops. That's why you are doing the minus 2 times 0.7. For the center tap transformer, just 2 diodes. For each half cycle, only 1 diode is on. Therefore, the VDC became 0.636 VM minus 0.7 only, not 2 times. That is the reason. Where VM is the peak value of the AC voltage. That's the diodes application in rectifier, which is a part of power supply. What do you have in a power supply? What is a power supply circuit? The adapter that I'm using now, it is a power supply. It takes AC from the wall, steps down the AC using a step-down transformer, and then rectifier makes a peak like you have seen just now. Then inside this, there should be a filter, capacitor filter, and then additional filter stage to make the output wave doesn't look like a wave but almost flat. And finally, there will be an IC voltage regulator. Diode clipper. What's a diode clipper? You can create a clipping circuit or a clipper circuit with diode. To clip means to clip or cut away. A diode clipper cuts away certain portion of the input. You can have a series clipper or you may even have a parallel clipper. What's happening in the series clipper? If you have a diode in the series clipper, it will clip or cut away any voltage that does not forward bias the diode. It is like a rectifier. See this circuit. Input voltage VI, diode, and across resistor R you have V out. This is the ground. Input voltage here is a square wave. Positive peak is a value of V volts. Negative peak is a negative V. They are both symmetrical, same value. During the positive half cycle, is the diode on or off? Diode is on, isn't it? Conducting. What is V out? This is ideal diode. VD is 0 when it is closed switch. VI minus 0 minus V out equals 0. V out is equal to V. Negative half cycle, what happens? For the negative half cycle, this is plus. This one polarity is minus. This is for the negative half cycle, negative input. Is the diode on? The diode is not on. Open switch, no current flows through R. Output voltage is 0. So this series clipper, what did it do? It clipped away the portion of the input that did not forward bias. Which portion of the input does not forward bias? The diode. The negative half cycle. On the output side, you see the negative half cycle is gone. It's clipped away. That's what a series diode clipper does. Today we will practice some more problems in the class using this type of circuit. What happens if the input voltage is less than 0.7? 0.3 maybe for a silicon. It will also not turn on. You need the sufficient voltage. This series clipper is true for all types of input waves. You are seeing a square wave. This one, what is it called? A triangular waveform. Same idea. One half cycle there's an input, the other half cycle not. You can also provide a sine wave, which will behave the same way. Then there is parallel clipper. Okay, before we go to parallel clipper, we can do another called a bias clipper. This is a series clipper. If you forget the 5 volt DC source inside, This is a series clipper, but we have added a 5-volt source. What is the reason for adding? By the way, adding a DC is called biasing. So why did we bias this clipper? If you add a DC source in series with the series clipper, it will change the forward bias of the diode. How does it change? It changes the biasing level. Okay. See the input peak, 20-volt peak positive and 20-volt negative. When the input voltage is 20 volt here, plus 20 volt, and this is an ideal diode, what is the output voltage? V out.
25 volts.
25. You can see the loop. Vi plus 5 minus V out equals 0. Therefore, V out is Vi plus 5. As you can see, it's already written 25 volt output. When the input now goes back to the opposite side and the input is at this point in time, the input voltage is 0. You think the diode will not turn on. That's what you think. But actually, what is the voltage across? Still did not change polarity. 0 plus 5. Here, 5 volt. Will the diode be on or off? It is still on. It is still on. Right? If it's silicon, 0.7 volt is enough. Germanium, 0.3 volt is enough. Gallium arsenide, you need only 1.2 volt. At the time when the input is 0 volt, you still have the 5 volt DC. It is still powering the diode on in a forward bias. That's why when it crosses the 0 point, just before crossing, you still have an output level 5 volt. Now, you think that when it goes to minus, immediately the diode should turn off. Will it turn off immediately? No. If it's at minus 1 volt, what happened? Minus 1 plus 5, still 4 volts, diode is on. Minus 3 plus 5 is positive 2, the diode will still be on. So it has to go to minus 5. The input has to go to this level of minus 5 when the diode can be completely off, because minus 5 plus 5 is 0. Now there is no bias. So you actually change the level of forward biasing. You shifted the level around by using a DC source with the clipper. This is a bias clipper. If you are given a bias clipper, you have to analyze the different voltage values and also using the KVL loop and determine when the diode will be off and when the diode will be on. Not as straightforward as the regular clipper with no bias. Any questions?
No.
No questions. So what else I was going to tell you after this? Now we have a parallel clipper. See the difference between series and parallel. Series clipper, you have after the input you have a diode, then you have the resistor or load. For parallel clipper, you have an input, you have a resistor, and the diode is connected parallelly with the output voltage. This is a parallel clipper. For the series clipper, I told you that it clips away the part of the input that does not forward bias it. For parallel clipper, it's exactly the opposite. It clips away the part of the input that will forward bias it. Let's see how. Positive cycle here, input voltage, this is the positive, and this negative. Is the diode on or off? Diode is on. Is it forward biased or reverse biased for the positive cycle? It is on. The diode is on. It is forward biased for the positive half cycle. What is the output voltage? You're taking the output voltage. Look at the node, the pair of nodes, parallel with the diode two end nodes. What is the voltage output for ideal diode?
0 volts.
0 volt. Short circuit volts 0. During the negative half cycle, what happens? I'm going to change the polarity now. This is minus, this will be plus. Now look at the situation, diode on or off? Off. Reverse bias, diode is off. In the middle, there's no current. So if you put a probe, P out with red and black, you're going to sense the minus voltage here, minus level, because this is the red probe of the voltmeter. This is the ground probe or the black probe. You're going to see minus V, because on the negative half cycle, the level is minus V. You're going to see an output. What happened now? For the parallel clipper, it clipped away the part that forward biased it. This one forward biased the diode, but on the output side, it is gone. It is working in opposite fashion of the series clipper. Doesn't matter if you take a triangular voltage or a sine voltage with the parallel clipper, the idea is the same. Can we have a biased parallel clipper same as a biased series clipper? Of course we can have. But make sure when you add the DC bias, additional DC, in order to change the level, you have to put the DC in the same node with the diode. Don't put the DC on the input side. Let me see if I can show you an example. Okay, this is in your textbook. It is giving you a summary of clipper circuits. What is the general waveform? What does it look like? Simple series clipper with ideal diode. If you have a diode like this, you can see positive half peak, it is off, negative half peak, it is showing you negative Vm. Then there is an example, generic example of a biased series clipper, ideal diode. What will happen during the positive peak and what will happen during the negative peak? You can even change the polarity of the battery inside or the DC source inside. This is for positive half cycle and negative half cycle. You can get both. What about this one? Positive half cycle is on, negative is off. It will be Vi minus V, the value, or Vm minus V. As you can see from this generic equation for positive half cycle, negative half cycle, that is off. Here, the input side, it will be Vm plus V when you change the polarity of the DC. So you have a larger peak. Similarly, for parallel clipper circuit, there is a generic slide that shows what happens. This is the one that we were talking about. Positive half cycle is on, short circuit, 0 volt. Negative half cycle, it is off, so you can sense the negative voltage Vm. You can do parallel clipper with biasing inside. What do you get for the positive half cycle now? This one is short, but you have V, right? This is V. From here to here is V. So instead of getting 0, you get a value, which is as presumably less than the input voltage. For the negative half cycle, you get minus Vm. Any questions for these slides? Are there any questions? No questions? What about this one?
A moment, sir.
You can practice at home. What about this one? This one. Positive half cycle, short, but you have a negative V here. So negative V. Negative half cycle, you're gonna get same as minus Vm. Quite strange looking waveform, this one. And if you have two parallel diodes in a clipper with biasing, what happens in the positive half cycle? You're gonna get V1 for the positive half cycle because this one is short, and then plus minus V1. For the negative half cycle, this one is open, the second one is closed, you get negative V2. So the waveform becomes like this, with some assumption that the absolute value of V1 is greater than the absolute value of V2. If you change the polarity of the diode, this is a negative bias, reverse bias, it will be positive half cycle, it will show you the peak, negative half cycle, it will not show anything. So I would encourage you to review these two slides just to give you a feel of how the output will be determined. And there is something called clamper. Before I go to clamper, I would like to see if we can do some practice. And also I will call the students. Okay, keep the screen like this while I find out the example on Microsoft Teams. Once I'm on that page, I will switch the screen over. So I'm right now loading. I'm trying to load your class notebook, which takes some time. And from the class notebook, I will find a content which I used to teach in the past for practicing the diode. Zener clipper. Okay, series clipper biased. Parallel clipper bias. So let me copy a few items to your main class page, and then we're gonna go there. In the meantime, if you have any questions from the clipper, you can ask me. There's nothing there. Problem 33 for the clipper. Okay, there is a practice problem from the textbook. I will also put that in. Move or copy. We have right here. Okay, now let's switch our screen. The screen sharing will now go to Microsoft Teams. Internal error. Can you see my screen?
Yes.
Okay, let's close this one. This is an example of a series clipper which is biased. I drew the input waveform. You can see it is a square wave, but it is not really symmetrical because on the input side, the peak of the square wave is 20 volts, and on the that is for the half cycle, positive half cycle. The negative half cycle is negative 10 volt. Input graph is VI, voltage versus time. The output has to be also voltage versus time. This is your circuit. And inside the circuit, there is a bias. DC bias is minus plus 5 volts. And you have your diode. Nothing is mentioned. I don't say it is silicon or germanium or what. So assume it's an ideal diode. Now I would like to ask students for the positive half cycle. Is Cora Witt here? I'm going from my last list. So Cora Witt, for the positive half cycle, what is the output voltage?
For the V0 line.
V0 or V out, yes. Think about it.
0.
Will it be 0 for the positive half cycle? Is the diode on or off for the positive half cycle? Determine from this circuit. In the positive half cycle, is the diode on or off?
It's on.
When it's on, do you have current flowing in the circuit? You said on. Your answer is correct. The diode is on. So will you have a loop? Current flow? Yes. What is the output voltage then? Taken from this node. What is the output voltage? Input voltage is now plus 20. What is the output voltage then?
25.
25 is the output voltage, positive half cycle. Okay. Next person, Pichayut.
Yes.
Now please consider the negative half cycle. Look at the input voltage at the negative half cycle, minus 10. So now it looks like this. Minus, plus, and then 10. Analyze the circuit and tell me if the diode is on or off.
From this circuit, right?
Yes, the one that I just drew. Negative half cycle, minus 10 volt input. In this case, the diode is on or off?
This one is off.
Off.
One that you
Yes.
off.
How do you say? How do you determine that it is off? At this point, I'm drawing a red arrow. At this point, what is the voltage that is the diode is getting at this point? Minus 10 plus 5. You're getting minus 5. Minus voltage, the diode is not going to turn on, which means there is no current in the circuit. It's an open switch. What is the output voltage finally?
0.
0 is the output voltage of negative half cycle. If I have to sketch the waveform, it's going to be like this. Let's draw some shading. This value is 25 output voltage, and this is 0. We have more examples to work on. Problem 33 is Clipper problem. This is taken from the textbook. It is not example 33. I believe it is problem number 33. Let's look at the circuit, all of us together. The problem is asking you, I believe, three things. Find the current when the circuit is on. Find the output voltage for positive and negative half cycles, and then finally draw or sketch the waveform. Okay, I'm going to the next student on the list, Mr. Jimma.
Yes, sir.
I would like you to consider the positive half cycle now, which is 12 volt plus 12 volt peak, only the positive half cycle, which means you have plus minus 12. In this case, when you look at the circuit for the positive half cycle, what is the status of the diode? Is it on or off?
On, sir.
The diode is on. As you can see, 12 volt comes directly to silicon. It needs only 0.7 volts to turn on. So it is on. Once the silicon is on, VD is 0.7 volt. Okay. Xuan Yuan,
Yes.
since we have determined that the current is flowing in the loop, can you find or calculate the value of the current that is flowing? What shall we do?
12 minus 0.7 and divide by 4 kilo ohm.
Very good. That's the correct answer. So how did he say it? Let me type in the value for you. I'm going to use the big font for the equation. KVL. I'm taking the plus sign, the outer sign. 12 minus the outer sign for the SI is minus 0.7 minus what? What volt is this? What is the equation for voltage? I times V equals IR. I times 2200, isn't it? Minus when the current flows here. When the current flows, this is plus, this is minus, this is plus, this is minus. I think now it is clear. Can everyone follow? What is the voltage across the second resistor? Current times resistor. This is the KVL equation. 12 minus 0.7 minus IR1 minus IR2 equals 0. What is the only unknown variable in this equation? Only I. So let's find out I. Minus 0.7 divided by, you have to add these two resistors, they are in series. It is 4000. How much is the current? 2.83 milliamp, I believe. Is it 2.83?
Yes.
Okay. Is Mr. Satawat here?
Yes, sir.
Satawat. So what is the output voltage during the positive half cycle? What is V out? I want you to look at the point where V out is taken. What is the output voltage? two ways actually of calculating. Both should give you the same answer. Determine the output voltage. And other people, you are welcome to try. And if you are done, you can ask me whether or not you should answer for me.
To be fine, VD first, Jan.
VD. VD, when it's turned on, it is 0.7 volt because it's silicon. VD, you already know it. So very simple circuit analysis actually. Where is V out taken? V out taken from here. This is the probe and this is the ground. You can calculate V out from this point to ground. First way. So this is actually the voltage across the resistor. What is the formula for voltage? You know the current now. Current times resistor. What is the voltage? 2.83 milliamp multiplied by 1.8 kilo ohm. What is it?
5.094.
Yeah, we will write 5.09 volt. You can even maybe write 5.1 if you try to round up. Let's keep it 5.09 volts. Or you see what is the node of V out? This and this, they are the same node. This node represents the voltage drop from the beginning all the way to end. If you do 12 minus 0.7 minus I times 2200, what do you get? Uh, 5.07, slightly different. Because I didn't take so many digits. Yeah, I took 2.83 milliamp. If you take exact result, 2.825. You're gonna get 5.085. You will get 5.09, round up. So two ways of finding the voltage. Always look at the circuit and see where I am asking you to take the voltage, or where the problem is asking you to take the voltage. All right, Yapeng?
Yes.
Now I'm going to erase a few things and we're gonna go to the negative half cycle. Yapeng, I want you to focus on the negative half cycle of the input. Here, negative 12 volt, which means the input is now like this, minus, plus, 12. What is V out now during the negative half cycle? What is the output voltage?
0.
0? 0 is correct answer. But why do you say that? What happens to the diode during the negative half cycle?
Off.
Off. So you can say open switch, which means there is no current flow. If there is no current flow, there is no voltage you can sense in this circuit for the output side. If you put a probe on the left hand side of the diode, you will see negative 12. But if you put a probe here on top of the 1.8 kilo ohm resistor to the ground, you will not see any voltage. So the output is 0. So if we were to sketch the output waveform compared with the input waveform, how do we do that? This is V out. If we sketch V out, This is the arrow, and x-axis is time in seconds, volts versus second. Here 12, so that was 5.09, maybe about here or less than that, doesn't matter, we're not drawing to scale. Positive half cycle 5.09, negative half cycle 0, and then it will keep repeating like this. The rest of the class, did you understand how this problem is solved?
Yes, Ajahn.
Yes, John.
Okay. We have one more problem to look at. This is 0. We have problem number 35, which is also a clipper. A clipper. Looks like this one is a parallel one with the bias. Let's increase the font size or the picture size. Home, insert. Why is it drawing? This should be okay for your eyes. I hope everyone can see. Seni, are you here? Seni?
Yes.
So look at the circuit again. The input is given. And this is the left two terminals are the input terminals. On the right hand side, you have the output terminals V out right here. I'm circling in red. During the positive half cycle, what is going to be the output voltage from this circuit? What happens during the positive half cycle?
4.7.
4.7. Very good. He's right. What happens? Let's see what happens. Plus anode, minus goes to cathode. So relatively, you have 8 here and you have plus 4. Be careful. In this case, be careful. There's a plus here. It might tell you that the cathode is connected with the plus volts, therefore it is off, but you have to look at the whole situation. Think of the two sides of diode getting some pressure. One is more positive, one is more negative. 8 volt plus here is more positive than 4 volts. So if you speak in relative terms, this side is still forward bias, like forward voltage, this is a reverse. Because if a current has to flow, it can flow from 8 to 4, a lower voltage level. If this was 9, maybe we have a problem. Okay, so this one is not that complicated. 8 volt plus here 4, it will still turn on. The diode is on. Once the diode is on, you're gonna get a voltage of 0.7 volt. 0.7 with the polarity like this, plus minus, which means this branch is active, and then you have a battery plus minus 4. When you are sensing the voltage, output voltage, you're gonna get the total voltage 4.7 volts for the positive half cycle. After Seni, we have Siripo.
Yes, Ajahn.
For you, the task is to find out the output voltage during the negative half cycle. So I will erase the picture for you so that it is clear again. What happens during the negative half cycle?
We are equal to 0.
You think V out equal to 0? Okay, we will come to your answer in a few moments. Is the diode on or off for the negative half cycle?
Diode is open อาจารย์
That is open. This is minus, this is plus, and you have 8. This has more pressure. Minus 8 has more pressure than plus 4. So overall, this is minus, this is plus. For sure, diode is open, which means this branch, nothing is happening, right? No current flow path. We can forget about the blue branch. Your voltmeter is connected like this. The red probe is the plus probe of the voltmeter, and then you're going to have a black probe, which is the COM or ground. The probe symbol or probe colors is like this. Now, if you ignore the branch in the middle, what will your voltmeter see?
Ignore what อาจารย์
The middle branch is not seeing anything.
อ๋อ
So what will the voltmeter see? The middle branch, there is no current.
is 0
No, the voltmeter will see this value, minus 8 volts.
อ๋อ โอเคครับ
In this case, the voltmeter will directly sense the negative peak. It is not coming from the diode, it is coming from the input. So if you try to draw the waveform again.
อ๋อ โอเคครับ I get it.
Output waveform, let me draw the output waveform. We have 4.7 and minus 8. So it will be something like this. The negative peak is definitely larger than the positive. This is positive 4.7. This one is negative 8. Again, if you want to find out at which point is negative 1, 2, 3, 4, we have to individually analyze with so many scenarios. But in general, the peak should look like this. You don't have 0 volts for the negative half cycle. That's the key idea here. V out, T. T is in seconds and V out is in volts. Let me see if we have some more. I think that's about it. This is a clipper circuit, parallel clipper with DC biasing. Series, okay, 2.4 and 2.9 we did in the past, previous class. Clamper, parallel clipper biased. The picture is totally gone from here. Series clipper we just did, parallel clipper, the picture is gone. So that's why I could not show you. 2.4, 2.9, simple circuits, resistance. The next topic is clamper. Maybe we do not go to detailed analysis today. In the next class we will do, but I still have to teach you the clamper for today's class. For that, I will again switch the screen. Screen sharing is now off. And screen sharing is going back to the PDF document. Any further questions about the clipper? No further questions?
if it parallel and it's open loop, so it don't have 0 for V out, right?
No, because then that if that loop is open, then there is no current flowing through that loop. So since you connect the Vout in parallel, it will go to the next part where it can see another voltage. But if the loop is on, then Vout will get directly from that loop.
โอเคครับอาจารย์ thank you ครับ
Okay. Clipper circuit, clamper. What's a clamper? The meaning of clamping is to shift. Clipper circuit and clamper circuit, fundamentally they're different. How? In the clipper circuit you have the input voltage, and then you have the diode, and then you have a load which is represented by a resistor. For the clamper, you have another component which is the capacitor. If you combine diode and capacitor and then connect with the load, this can be used to shift or to clamp an AC signal to a different DC level, specific DC level. It is shifting the DC level. That's why it is called a clamper. The basic construction is like this. Immediately after the input, you have a capacitor. Then you have a diode. Then you have a resistor. If the symbol of capacitor is like this, we can say plus, minus, because parallel plate capacitor, the straight line is the plus plate and the curved line represents the negative plate. This is just for understanding first. Later on, you will see that it might change. But this is from the construction of capacitor. There are multiple parts of the analysis. There are 5 parts actually. The lecture slide shows you only 3. First, I'll tell you the number 4 and number 5. First, you have to start the analysis from the portion of the input signal which will forward bias the diode. So look at the input signal. Here, the input signal. Positive peak, negative peak, this is a square wave, which means you have plus, minus. And then on the second half cycle, the negative half cycle, you have minus, plus. Look at the diode orientation and tell me which half cycle the diode will be forward biased. During which half cycle?
Positive.
Positive half cycle, because it is anode, it is cathode, which means you start analysis with the part where the diode is forward biased. Now, what is the behavior of a capacitor? When you put voltage across the capacitor, it keeps charging to that volt, but it takes some time because there is something called the time constant. Depending on a resistor and capacitor value, it takes 5 time constants to fully charge. But when the diode is on, we have to make an assumption that capacitor will immediately charge instantaneously to the voltage level, which will be determined by the surrounding network. What is the meaning of that? Look at the surrounding network during the positive half cycle. Positive half cycle, diode is on, so you have plus, minus VD. When the diode is on, VD. Plus, minus VI. In which direction the current is going to flow? Clockwise, right? From plus to minus. And then we call the voltage across the capacitor VC. The left-hand side is a complete loop. Look at R. Okay, some antivirus is disturbing me. It's okay. Can you still see my screen?
Yes, sir.
Look at R. Parallel node with the diode. Voltage output is taken across R, which is also parallel to here. So this is parallel voltage sensing. The diode is on. What is the voltage of diode now? Ideal diode?
0
0. What is the KVL loop equation? VI minus VC minus, you can say 0 equals 0. Or VI minus VC minus V out, because VD is V out, same. This one and this one and this one, they're the same. You can say VI minus VC minus V out equals 0, right? Or you can say, instead of V out, you can say VD. VI minus VC minus 0 equals 0. KVL loop for the left loop. So what is VC then? From this equation, VI minus VC minus 0 equals 0. What is VC? VC is same as VI. What is the value of VI? V. What is the output voltage when the diode is on? What is the output voltage across resistor R? 0. Short circuit, 0. Here is 0. Parallel, 0. Can everyone follow? Did you understand why VC equals V from the equation?
Yes, sir.
Okay, so you have analyzed the positive half cycle or the half cycle where the diode is turned on. Now, when the diode is turned on, the capacitor got the voltage VC equals V with this polarity, plus minus, because current is flowing clockwise. We finished the 1/2 cycle. And capacitor voltage is this, plus minus V. Now we're going to analyze the other half cycle when the diode is off, which means this is negative VI, this is plus. But you have to assume at this stage that when the capacitor was charging, when the diode was on, whatever voltage and polarity it got, it will remain the same. Capacitor holds its established voltage level and established polarity. It doesn't say on the slide, but you should remember. Everyone okay? Now, negative half cycle. Diode is on or off?
Off.
Off, which means this node is open, nothing happens. So where the current is going to flow, there's a loop, outer loop, isn't it? Even the inside is open, but the outside is behaving like a closed loop because you have a resistor there. You have a resistor, you have a path. Now you have an outside path that can act as a path for the current to flow. Now you tell me what is V out. V out polarity is the same. So number 4, step number 4 is an instruction, which means during the entire time, you must maintain the awareness. You should know how you took the polarity and where is the current flowing, such as this. V out is plus minus, VC is like plus minus V. You have to remember this. That is step number 4. Look at the equation. Minus VI minus V minus V out equals 0, isn't it, in the loop? What is V out then? What is V out? From the KVL, what is V out?
V out equals V.
Let you listen the equation again. You can say minus V, because VI equals capital V. This is, I'm taking here, or you can also take counterclockwise. I'm taking clockwise the loop. Minus V, and then minus V minus V out equals 0. If you take V out to the right hand side, what does it equal to? V out equals
minus 2V.
minus 2V. Minus 2V. See, here, V out on the negative half cycle is minus 2V. That's the correct answer. Step number 5, last step, also not shown on the slide. It is on your textbook. There is a final check that you need to do. That is step number 5. The total swing of the input voltage must match the total swing of the output voltage. The swing is determined from one extreme peak to the other extreme peak. Look at the input voltage. How much it has swing from 0? How many volts? V volts, right? Here is V. And from here to here, ignore the negative sign. What is the amount that it goes on the negative side? Here it goes by V volts. Here it goes by V volts. And two extreme. This is the maximum peak it will reach. This is the maximum negative peak it will reach. So how much is the total swing?
2
2
volts.
volts, 2 V. Let's say V is 4. Let's say V is 2. 2 and 2, 4 volts. Or you can say 1 and 1. So 2V. We don't know V yet. They didn't give a number. What is the output swing, total output swing? The amount, not the sign. Ignore the sign. What is the amount? 2 times V. This is the final check for the clamper circuit. Step number 5, you must check the total input swing matching the total output swing. If this matches, then your analysis is correct. If it doesn't match, then you have done something wrong during the analysis. Today, I'll leave it at this. The next class, we can do clamper problems and then deep into Zener. Then this chapter is finished and you're gonna get a homework on next Tuesday. Did you have any question about the clamper?
อาจารย์ is always equal to VI เหรอครับ for clamper
For which one?
For when in the clamper is always equal to VI or not?
No, not equal to VI because VI can change. See? Not always. You can if you want to determine the polarity of the capacitor. Okay, let's see. This one quickly I'll tell you, but next class we will do. Positive half cycle, not on. Negative half cycle, it is on, right? The diode. So we start analysis from the negative half cycle. In which direction the current will flow in the negative half cycle? It will flow like this. When it flows, polarity of capacitor like this, plus, minus. Now you see, negative half cycle, 20 minus 10 minus VC equals 0. So VC equals how much?
So we are always equal to 0 when it's like this.
Yes, we will do in the next class.
Okay, sir.
Okay, again you see negative half cycle. What happens? This is short negative half cycle. You get minus 10 volt output, which is right here. But what is the polarity of VC? VI minus 10 minus VC equals 0. VI is 20. So VC is minus plus 10. Now if you do the positive half cycle, you get 20 plus 10 minus V out is 0. 20 plus 10 is 30. We'll see in the next class. Don't worry, we'll do maybe 2 clamper examples. Starting the attendance call. Balan?
Yes, teacher.
Hirawut?
ครับอาจารย์
Apatra?
Yes.
Pakon?
Yes.
Rajay?
Yes, Ajahn.
Pernikahan?
Yes ค่ะ
Michelle?
Yes ค่ะ
Phil?
Yes, sir.
Nikon?
Yes sir
Wisarut?
Yes.
Yucheng?
Yes, teacher.
Sheshehan? Yes. Sheshehan
Yes, อาจารย์ Yes, อาจารย์
Patompong
Here ครับ
Kungsu. Is Kungsu here?
Yes, sir.
Martin
Yes, John.
Kolawit. Kolawit is here. Pichayut is here.
Yes.
And Jimma, Sunyuan, they're all here. Satawat is here. Yapeng is here. Seni and Siripov is here because you participated. V2,
Yes, teacher.
San An.
Yes.
Waramet,
Yes.
Naba 1.
Yes, here.
Natapok,
Yes, I'm here.
Warapat,
Present, Ajahn.
Nataya,
Yes, teacher.
Pichayapon,
Yes, sir.
Komchan,
Yes, I am here.
Piradon,
Yes, I'm here.
Kitsanapong.
I'm here, teacher.
Okay, Atit,
Yes sir
Tasin,
Yes.
Sukaina. Where is Sukaina? Is Sukaina here?
Yes.
Okay, Sirin.
Yes.
Is there anyone I missed?
Yeah.
Sukaina, I got you. Anyone else? No one else. The attendance check is complete for everyone. Everybody is present today. See you next week.
Thank you, sir.
Okay. Welcome.
Ajahn,
Yes.
can I ask you about question problem 33?
33. Okay.
Yes, about the output, why the output, like there's something like no voltage there. Can you show me again? Can you explain it again?
Okay, I'm gonna go to the screen. Here is problem 33 on the screen, as you can see. Can you see the screen?
Yes.
Okay, I'm gonna show you the one we did in the class. You're asking why there is no voltage for negative half cycle?
Yes, on the negative half cycle.
On the negative half cycle, yes, it is minus 12 volt now. This is the negative half cycle. The input is like this, minus and plus. When you put minus 12 volt on the anode, and this is the ground, this is the ground, which is kind of at 0, so minus 12, the diode is not on, the diode is open. It is like an open circuit. Once you have an open circuit, what happens? Is there any current?
No.
No current. V out you can take from here, from this point to this point. That is the V out actually in this circuit. So if there is no current through the resistor, there will be no voltage according to Ohm's law. And there is no voltage drop here. Nothing will be sensed at this node. No voltage. Still confused?
So for this one, for the negative one, I just write there's no current, right? So that is why the output for that is 0.
Yeah, but what if I ask you to take V out here? If I take V out here, what will you tell me?
Then it should be minus 12 voltage.
Minus 12, right? Yes.
Okay.
If you bring the probe from the right side to this side, the left side of the diode, you're gonna see minus 12.
But in the case that it is parallel, so I can take the V out from the another one, right? If there's
you can look at the parallel node and see what is going on. In this case, it is not parallel, it is a series.
Okay, so in this one, there's no current flow in the reverse one, right?
No, reverse one, the circuit is open. No current.
Thank you so much, Ajahn.
You're welcome. Okay, if no one else has any questions, you are free to leave or go to your next class.
Thank you, Kap.
Welcome.
sir.
I'm going to close the session. Okay.